Hey everybody! The purpose of this video is to get you some solutions to the E6 quiz from two parameters. It's the one about two-tailed versus one-tailed tests. So the idea is to explore why two-tailed tests are sometimes used more exclusively for certain statisticians. So the first thing I told you to do was to make up data. We're using two proportions here, which is the easiest way to do it. Although please realize that whether we use two proportions or two means, or one mean or one proportion, it really doesn't matter. It's valid across the board. This is just the easiest one to run on two. So if you've got x1 and n1 being 15 over 100 and x2 over n2 being 25 over 100, these are the ones I jumped with. I tried the easiest numbers I can come up with. If you run this guy, I ran first a 2 prop z int. So let's go into there first and get you some values here. So your two, and you realize too that your solutions are going to be different than mine unless you pick the exact same numbers I did, which is possible. If we run a 2 prop z int, I got to figure out where that is. It's way down here. There we go. On 15 versus 25 at 95% confidence, my interval is between negative 21% and 1%. So I got negative 21% and 1%. And the reason that doesn't show a significant difference, can you tell? Check out the interval. Since it goes, oh, hello big yoga ball. Negative 21% through 0.1%, it crosses through the number 0. Since it crosses through the number 0, there's no significant difference between the two, no statistically significant difference, because it's unclear whether it's negative or positive since it crosses through 0. So that's part A. There's no significant difference. You'll get a replicated result if you run a 2 prop z test two-tailed. So if you run a two-tailed test on this bad boy, whoops, I hit the wrong button there. Hang on. 2 prop z test, same exact result. Click through. Alright, so the two-tailed test, we end up with a test statistic of negative 1.77, which is actually getting pretty close to 2 standard deviations. But the p-value is 7.7%, which by, you know, it's bigger than 5, so therefore we would believe that the research hypothesis isn't worth believing. In other words, we would fail to reject the null. It's too hard to believe there's a difference in these two things. It's a 10 percentage point difference, but it's not a big enough difference to see. So if you correspond that to a graph, let's draw a graph to go with it. Okay, you end up with, here's the 0 difference, pretend that's in the middle. A negative 1.77 is down here. Two-tailed test replicates to positive 1.77, and essentially what you've done is you've shaded so much area that it becomes too hard to believe that there's actually anything going on differently between 15 and 25. So that's that. Okay? Now if you replicate the same exact test in part C as a one-tailed, right? I said, yes, one being greater than the other. So if you test that 2 is bigger than 1, okay? One-tailed. Well, you don't even have to run the TI to figure out what's going to happen here. The test statistic's going to be the same. I mean, it has to be the same. If you think about the way you create a test statistic, it's going to be the difference in the sample proportions over the standard error. It doesn't matter if you test it one or two-tailed. That is going to generate that value right there. So you're definitely in the same place. The difference is the graph. If you pick less than, okay, if you actually pick that it's less than 15 is less than 25%, then the graph is going to look similar. The difference being that the negative 1.77 down here is only going to shade this side, You're not going to replicate it on that side too, which means that you're going to end up with half the p-value you had before, which means your p-value is going to come in at half of 7.7, which trips into below 5%, which all of a sudden looks significant. Hopefully that makes sense. So if this p-value here is bigger than 5%, but less than 10%, running a one-tailed test automatically has to be less than 5% mathematically. So you can see there's something potentially fishy right there. We'll come back to that in a second. D, which of the following is always true? If you get statistical significance with a one-tailed test, you will also get statistical significance with a two-tailed test. Well, that we just proved that's not true, because this one has statistical significance, but it doesn't carry over to the two-tailed. So that one's not always true. If you get statistical significance with a two-tailed test, you will also get statistical significance with a one-tailed. Now, this doesn't actually illustrate that, because we did not get statistical significance up here with the two-tailed test. However, if we had gotten a p-value less than 5% up here, and you cut it in half, it's still got to be less than 5% down there. So definitely number 2 there is the correct one of the two statements. Makes sense, hopefully. And the crux here is part E. Why is it that some statisticians only run two-tailed tests? Well, it's harder to get a smaller p-value. So if you really, really want to avoid a type 1 error, you're going to want to default to getting as extreme a value as possible before you actually believe it. So a two-tailed test is going to enable you to do that, because it's going to force you to be outlierish as possible, if that's even a phrase, I just made it up, I guess. Outlierish as possible to drive this thing down. It's harder to get a less than 5%, or actually less than any percent that you need, working a two-tailed test versus a one-tailed test. So, hopefully that helped. We'll see you in class.